Hello, math students. Today we're going to be going over representing transformations in a plane. We're going to be going over the tutorial as well as the mastery test, but a couple things to keep in mind for this one is there's going to be a total of 4 different transformations that we're going to talk about. Don't focus on all 4. We're going to focus on one at a time. So the first one we're going to talk about is translations. And honestly, this is the simplest transformation that we can do with a shape. Now, the idea of transformations is very important, has tons of applications all across real world situations. Plenty of jobs have to utilize this sort of thing. So it's very important that you understand how this works. And also it's a very important geometric concept going forward. So let's go ahead and go to page 6 of the tutorial. Let me move my face here. And let's go ahead and start with question 1 here. Once again, you're going to be using GeoGebra like in the last lesson, so make sure that you open that up and you have a good understanding of GeoGebra. So you're going to open this translations GeoGebra here. And you should see 4 triangles here. All these triangles are the exact same. And this is an important concept in geometry, is when 2 shapes or 2 figures have the exact same measurements, we call them congruent. So I can say that these 4 triangles are congruent to each other. Okay. Now let's talk about what translations are all about. So let's go ahead and go to question 1. It says move triangle ABC. Notice how I read that. They put a little triangle symbol and then ABC. So that's how you read that sort of thing. So when you see that little triangle in front, that means they're talking about a triangle. So move triangle ABC so that it lies on top of triangle DEF, triangle GHI, and triangle JKL. How many units do you have to move triangle ABC from its original location to coincide with each of the other triangles? Specify how triangle ABC moves up, down, left, or right. Okay, so that was a mouthful, but let's go ahead and look at that GeoGebra and first identify triangle ABC. So triangle ABC is this one here. So this is the one in quadrant 1 right here. We could see A is at point 1, 2, B is at 2, 3, and C is at 3, 1. So this triangle ABC is our starting triangle. Now what we want to do is we want to translate it or shift it so that it coincides or lands up on top of each of the other triangles. So the first one we want to talk about is going from triangle ABC to triangle DEF. So where's triangle DEF? Well, that's one right here below. So how would I move triangle ABC so that it coincides with triangle DEF? So notice I can, if you click and drag, you can pick up a version of triangle ABC on the GeoGebra. So I can click and drag. And so how would I move this triangle so that it coincides with this triangle? Well, I would move it downward, right? So I would move it downward to make it coincide with that. Notice how I can move one triangle perfectly on top of the other triangle. That shows me that the 2 triangles are congruent, which makes sense because if they're the same size, same shape, congruent, they should be able to land or coincide perfectly on top of each other. Okay, so we needed to move triangle ABC downwards. Now, how much downwards? So we needed to move it. Notice if I'm looking at each of the coordinate points, I could maybe look at coordinate point B. It's going to coincide with coordinate point E there. So how much do I have to move point B downwards to get to point E? Well, notice B is at a y coordinate of 3, but E is at a y coordinate of 0. So I need to move it down by 3 to coincide there. And the same is with C, right? Notice C went from +1 here to -2. So that's downwards of 3. Same with A. So each point is translated downwards 3 units. So that's what we're going to say here. So for triangle DEF, we had to move triangle ABC down 3 units. okay? And whenever we shift a shape, just moving it left, right, up, or down, we call that translation, which is what this is all about, translation. Okay, now let's go back, put our triangle A prime, B prime, C prime back on ABC here. Now let's move this triangle to coincide with HIG. So how would we move our triangle ABC? Well, we'd have to move it to the left. How much to the left? Well, let's see. B coincides with H. So how much would I have to shift point B over to the left to coincide with point H? Well, notice B's x coordinate is at 2 and H's is at -3. So that would have to move over 1, 2, 3, 4, 5. So 5 to the left. Maybe I can make grid lines here. I wonder. Not seeing it. Oh, here we go. All right, maybe that's easier to see with grid lines. You can count from B to H, it's 1, 2, 3, 4, 5 to the left. Okay, so we needed to translate triangle ABC to the left 5 units. Okay, so we translated triangle ABC to the left 5 units to perfectly coincide with triangle GHI. Now, what about for triangle JKL? This one's a little more complicated, but not too bad. So let's go back to the start. How would I move or translate triangle ABC to perfectly line on top of triangle JKL? Well, notice I would have to move to the left and down, right? So in this case, we would move to the left how much? 1 unit, 2 units, 3 units, 4 units. So to the left 4, to the left 4. So I'm going to put over here, left 4 units. And we have to shift it down, right? So down how many units? Let's find out. So down 1, 2, 3, 4, 5 units. Okay. So we had to shift left 4 units and down 5 units. Okay. Shifting it is, I'm using that word, but that translating it means the same thing. So translation is just a shift of the shape, moving it left or right or up or down, but it's not spinning it or anything like that. Okay. What are the coordinates for vertices triangle A prime, B prime, C prime after each movement? Okay, so basically we would need to find the coordinates for DEF essentially. So what we could say is A prime, and then we're going to put what coordinates it is. Okay, then we also would say B prime and put the coordinates, and as well as C prime, put the coordinates. Maybe I'll put a, looks good like that, I think. Maybe a couple spaces in between, so it's a little spread out. Okay, I think that'll look nice. I want you to, we're gonna copy and paste this and put this into these other 2 fields as well. We're gonna put the coordinates here though, okay? So when we look at triangle DEF, let's going back to here. Notice A prime corresponds with point D, right? They're the same. So what are the coordinates of point A prime here, or in other words, point D? Well, it's 1, -1. So we're going to put here 1, -1. Remember, when we do coordinate points, we always do the x coordinate first, then the y coordinate. So you can see this point here is 1 on the x-axis and then -1 on the y-axis. Okay, what about point B prime, or in other words, point E in this case? Well, that would be 2 on the x-axis, 0 on the y. So 2, 0. And for C prime, it's right here where point F is. So 3, -2. Okay. Now we want to find the coordinates for A prime, B prime, C prime once again, but when it's coincided with triangle GHI. So let's go ahead and move our triangle to GHI, okay, just like this. And we want to find the coordinates, once again, for each of those points. So for point G, for point H, and for point I. So A prime is where point G is. That's at -4, 2. -4 on the x-axis, 2 on the y-axis. -4, 2 is what we'll put there. Now, what about for B prime in this situation? Well, that's where H is. So that's -3, +3. -3, 3. And C prime in this case, that's at -2, 1. Notice it's where I is. -2, 1. Okay. Now I'm going to let you do for triangle JKL. I'm going to let you try that on your own. But go ahead and move this triangle so that it's on here. Then tell me the coordinates for A prime, or in other words, point J, B prime, and C prime. Okay? Okay. Let's see. All right. Find the distance from vertices triangle ABC to the corresponding vertices of the other 3 triangles and enter them in the table. For triangle JKL, you'll need to use the distance formula. Notice they put a distance formula here. D equals the square root, parentheses x1 minus x2 squared plus y1 minus y2 squared. Okay, that's the distance formula. We're not going to use that, so don't worry too much. Okay, but we're going to verify our calculations using the tools available in GeoGebra. We're just going to do this second part, using the tools that GeoGebra has to help us find distance. Okay, so you're going to put the same value for both of these, essentially. Okay, but let's go ahead and see. Original vertex A to D. So if you want to go from A to D, well, this one doesn't require any calculations at all, right? How far is point A from point D, right? You could just count how many units away it is. 1, 2, 3 units away. So that's, we're going to put 3 units, just like that. Okay. Now, if you can't see that that's 3 units, another way you could do it is by using GeoGebra's tools. So if you look at up here, you can click on here, then you can click on distance or length, which is right here. You click on point A, then point D, and it'll tell you the distance just like that. Okay, so that's another thing you can practice, because finding the distance or length in GeoGebra is certainly something you're going to be using often. Okay. Now, what's the distance from point B to point E? Well, it should be the same as 3, right? Down 1, 2, 3, which makes sense because we translated down 3 units. So that's going to be 3 here as well, from D to E, as well as from C to F. Okay, what about A to G? So going from point A to point G, how much is that translated? Well, 5 to the left, right? So the distance there is 1, 2, 3, 4, 5 units. Simple as that. And it'll be the same for the rest of this triangle. Right, from B to H and from C to I, because the entire shape was translated 5 to the left. Okay. Now this last one's a little bit trickier, but we can use GeoGebra to help us out. So we're going to go ahead and find the distance from A, from A to J, from B to K, and from C to L. Now one thing we've learned is it should be the same throughout, right? Whatever the distance for one of those should be the same for each of them. Let's go distance and length. Click on A, then J, and it should say AJ equals 6.4. Notice B to K is also 6.4. C to L is also 6.4. So it should be 6.4 across the board there. So go ahead and fill out this, finish filling that out. What do you observe about the distances between the 3 pairs of corresponding vertices for each movement? So for that, you should say the distance from the triangle ABC to the destination triangle, or in other words, the image triangle, is the same throughout. So that's what I want you to say there. So the distance between triangle ABC to whichever translated triangle is the same throughout. Then, based on your observations, how would you define translation? So what is a translation then? It's a movement of a shape, but it conserves basically its orientation, right? So if it's oriented like this, then it stays like that, right? But it doesn't like rotate or anything like that. How can you extend what you know about the vertices of a shape to all the points on a shape during translation? So what we would say is that every point along the original shape is translated the same amount to get to the image. Okay. Again, each point along the original shape is translated the same amount to get to the image. So I explained those three problems there. You might have to rewind the video and type it in, but rewind and pause or whatever, but go ahead and fill that out. Try to answer in your own words. Okay, let's go ahead and move on. And we're going to talk about so here's talking about translation some more. Here, this original triangle ABC, was translated up 3 and then to the right 1. You can see each point is translated up 3 to the right 1. Okay. So let's go ahead and take a look at this problem right here on page 8. Polygon ABCD is translated to create polygon A prime, B prime, C prime, D prime. So a couple things I want to note here is that anytime you translate, but this is going to go for all of our transformations, translation, rotation, reflection, dilation, the new shape always has those apostrophes. Okay, notice it's like A apostrophe B apostrophe, but we call those primes. So we call that A prime, B prime, C prime, D prime. Okay, also the original shape we call the pre-image. So in this one's case, the pre-image is ABCD, and that's creating the image A prime, B prime, C prime, D prime. Okay, so point A is located at 1, 5. And point A prime, so on the image, is located at -2, 3. Which expression defines the transformation of any point x, y to x prime, y prime on the polygons? Okay, so basically what it's saying is our original point was 1, 5. Our new point is -2, 3. So how was it translated? Did it translate left or right? Did it translate up or down? So a couple things to think about is it went from an x coordinate of 1 to an x coordinate of -2. You see that? So that means it moved from 1 to -2. So that's moving 3 to the left, 3 to the left. In other words, it subtracted 3 on the x coordinate. What about for the y coordinate? Notice it went from 5 to 3. Well, that's moving downwards by 2. So we would say this one right here. Another way to think about it is you can go actually graph the coordinate points and then just count the movement from one to the other. So if I did 1, 5, I can show this here on Desmos, 1, 5. And then the other point was -2, 3. Whoop. Now we can see our 2 points here. Notice to go from the red point to the blue point, it moved to the left 3 units and then down 2, which is exactly what we said, right? To the left 3 units and down 2. Okay. Again, that's called a translation when we're just moving the shape. Okay. Polygon ABCD is translated to create polygon A prime, B prime, C prime, D prime. A is located at 1, 5, and A prime is at -2, 1. What is the distance from B to B prime? So the one thing to think about is the distance between A and A prime is the same as the distance between B and B prime, or C and C prime, or any point on the pre-image to any point on the image. That distance will be conserved. So from point A, we could see at 1, 5. from point A prime is at -2, 1. One thing we could do to find distance is we can use that distance formula that we saw earlier, but there's a much simpler way if you remember how to use your GeoGebra. You can just graph the 2 coordinate points and then find distance or length. So that's what we're going to do. Our points are 1, 5 and -2, 1. Let me write that down. If you want, you can open a new tab of GeoGebra. You just go to geogebra.com/classic, and that'll open a new GeoGebra tab, but you could use the old one that we were using earlier as well. So I'm going to graph my 2 points, 1, 5. So you can go to the point tool, and we want to point at 1, 5, which is over here, 1, 5. And then our other point was -2, 1. Okay, it's where I is essentially. So we'd find the distance from M to I in this case. And find distance using GeoGebra. We go to here, go to distance or length. And we can see that distance there is 5. Okay, which will be the same distance from B to B prime or C to C prime. Okay, or any point from the pre-image to the image. Okay, so that was our first type of transformations. It's called a translation. It's the simplest kind. It's just shifting it left to right. Look, notice I'm translating my screen right now, my face. But what about the next type is called a reflection. So we're going to go over how to do reflections here. So again, we're going to use a GeoGebra. So we're going to click on this. By the way, if you're not familiar with the GeoGebra, you're going to need to. So please follow along on all these GeoGebra. Make sure to open it up and do it on your own so you can get the fullest understanding. To produce a reflection or mirror image, you need to specify a line of reflection. When mirroring objects on a plane, a line of reflection is represented by a straight line. Move polygon ABCD around the coordinate plane and describe the 3 lines of reflection that you see. So we go back to this GeoGebra, and you can move around this polygon here, ABCD. But I want you to notice that when I move this one, all of these reflected ones move as well. Okay. Notice that also each of these images are a reflection of ABCD, a reflection of this pre-image. So what is the line of reflection for this polygon here? Well, in this one's case, the line of reflection is the y-axis. So the y-axis is acting as a mirror in this case, right? You can see that for these 2 shapes. What about for our pre-image to this one here? Well, in this one's case, that's reflected across the x-axis. So the line of reflection for these 2 is the x-axis. And then for this one, the line of reflection is this line right here, line EF. Okay. Notice how if I move my pre-image closer, the image also comes closer. If I move my pre-image away, then the image also moves farther away. That's a key aspect with reflection. Whatever the distance to the line of reflection, then the distance away from the line of reflection is the same. Okay, so in other words, the distance from B to the line of reflection is the same as B prime to the line of reflection. Okay, so what are the 3 lines of reflections I just described? Well, there was the y-axis, the x-axis, and then line EF. Okay, so that's what you want to say there for question 1. Place the vertices of polygon ABCD wherever you wish, and record the coordinates of its vertices. What are the coordinates of the vertices of the reflected polygons when the x-axis and y-axis are used as the lines of reflection? Record the coordinates in the table. So you can move this polygon to wherever you want, but I'm going to actually move it to, let's say, right here. Okay. Now, notice there are no grid lines, but we can make there be grid lines. Let's see. There we go. Okay, so now there are grid lines, which is good. Now it's easier to count where each of the coordinate points are. So notice for our pre-image, A is at 2, 2. So we would put for A, that's at 2, 2. Okay, let's go ahead and put the coordinate points for the rest of the points on the pre-image. What about B? What's this one's coordinate? Well, it's 3 on the x-axis, 4 on the y, so 3, 4. Notice with coordinate points, I always put them in parentheses. That's generally how it's written. Point C is right here, so that's at 4, 3. Now, if you put your quadrilateral at a different location, your pre-image at a different location, you may get different numbers here. And then D here is at 3, 2. Okay, just like that. Now, what are the coordinates for A sub x? So basically this is A prime when it's reflected across the x-axis. So that's these ones down here, right? So what's A sub x is 2, -2. Okay. What about B sub x? Well, that's at 3, -4. Okay. Fill in the other 2 points as well. Then we're going to do the same for the one that's reflected across the y-axis. So in this one's case, A sub y, it's right here. This is at -2, 2. Okay. What about B sub y? That's going to be at -3, 4. Okay. And then fill in the rest. Review your answers to question 2. What happens to the coordinates of the shape when the shape reflects across the x-axis? What happens to the coordinates when the shape reflects across the y-axis? So hopefully you notice some patterns here. Notice that when I reflect across the x-axis, I'm looking at this A sub x, B sub x, so on. Notice the x-coordinate stays the same, but the y-coordinate changes signs. Notice it went from 2 on the y-coordinate to -2. Similarly, for point B, the x-coordinate is the same, but the y-coordinate went from 4 to -4. So we could say that. We could say, when reflecting a shape across the x-axis, the x-coordinate remains the same, and the y-coordinate changes signs. And when I say changes signs, meaning from positive to negative or from negative to positive. Now, what about when reflecting across the y-axis? So when reflecting across the y-axis, what happens? So I'm going to let you figure that out on your own, but looking at these patterns, notice for my original point, it was 2, 2. Then when I reflect across the y-axis, it's -2, 2. Similarly, for point B, it was 3, 4, but when I reflected across the y-axis, it was -3, 4. So what happened to my x coordinate? What happened to the y coordinate? Okay. I'll let you explain the rest of that sentence there. Next question, 4. Move point F to the origin 0, 0, so that the equation of line EF is y equals x. Okay, so let's go back to GeoGebra and show that. So we're going to move point F, so it's at 0, 0. Okay, so now we have EF, and the equation for this line is y equals x. Okay. Now record the coordinates of the vertices of the polygon ABCD with the coordinates of the vertices of the reflected polygon A sub EF, B sub EF, C sub EF, and D sub EF, where line EF is the line of reflection. Okay, so I'm going to move, let's go ahead and move our ABCD. We're going to move it, how about to right here? Yeah, this looks good. So now point A is at 1, 3. A is at 1, 3. B is at 2, 5. And write down the other two coordinates. So for coordinate point C and point D. Okay. Then we want to look at the coordinates for A sub EF, B sub EF, and so on. So let's go ahead and look at that. So A sub EF is at 3, 1. Parentheses 3, 1. The new point B for the image is going to be at 5, 2. All right, 5, 2. So just hopefully you filled out the rest. So go ahead and pause the video and finish filling out the rest for both the ABCD as well as the image after reflecting across EF. Now, hopefully you notice a pattern here because we're going to have to explain it here in question 5. Review your answer from question 4. What happened to the coordinates of the shape when the shape reflects across the line y equals x? Explain. So notice that the coordinate point for A went from 1, 3 to 3, 1. Similarly, B went from 2, 5 to 5, 2. So what happens with my x and y coordinates when I reflect across that line? Well, the x and y coordinates essentially flip, right? So that's what I want you to explain there. Okay. Question 6. Draw a line segment between each vertex of ABCD with the corresponding vertex on the image across EF. Okay, so let's go ahead and draw those segments. So what we're going to do is back on GeoGebra here, you want to go to the segment tool. So where's that? So that's going to go, you go to this line here, you're going to go down to where it says segment. And we're going to connect each point A to A sub EF, D, C, and B, each to their corresponding pre-image to image, just like that. Okay, good. There are 4 line segments in all. We did that, great. Then move polygon ABCD around the coordinate plane. What do you observe about the angle formed between the line segments you drew and the line of reflection EF? Use the tools available on GeoGebra to confirm your hypothesis. So go to the move tool, and when I move this around, what do we notice? The main thing they want you to see is the angle that's formed between this line and our lines that connect our image and pre-image. So the line of reflection and this line, they form what kind of an angle? So maybe we can see that here, angle, and we can say, click here, click here, click here. Will it give me that? No, it will not. Back. I could put a point. I could put a point where they cross, intersection points like that. Okay. Then maybe I can go to this angle, and and go EIC like that, EHD like that, EGA like that. Okay, now what do we notice? What do we notice here? What do we notice about these angle measures? Well, they're all 90 degrees, aren't they? So what does that tell us? Well, that tells us that the line that connects our pre-image to image is perpendicular to the line of reflection. Remember, perpendicular means they cross at a 90-degree angle. We covered that in the last lesson. So each segment that connects the pre-image to the image is perpendicular to the line of reflection. Okay, so that's what I want you to state here. Each segment that connects the pre-image to the image is perpendicular to the line of reflection. Remember, that means that they cross at a right angle, a 90-degree angle. Okay. Let's go ahead and go to question 7 here. Move polygon ABCD to a location of your choice on the coordinate plane and change the orientation of EF. Be sure that the pre-image ABCD does not overlap the image when you're through. Next, find the perpendicular distance between each vertex ABCD and EF. Enter the values in the table. Do the same for the perpendicular distance between each vertex of the reflected shape. Okay, this is a lot of words. Record all your answers to 1 decimal place. All right, this is a lot of words, but it'll make sense in just a second. So basically what they're asking in the most complicated way possible is, let's go ahead and move our shape a little bit. We're actually going to move our line of reflection a little bit. So that way, maybe like this. Okay. And I'm going to go ahead and also I'm going to add another point. Let's add another point right here. Okay. And I notice these are all perpendicular. So that's good. That's what we want. Well, this should say 90, but it's kind of weird. But now what they want you to see is the distance from our pre-image to the line of reflection, line EF. Also the distance from the image to line EF. So let me show you what I mean. You're going to go to this tool right here, go to distance or length. And so we're going to go from point B to point J here. And it should say, well, your number may be different depending on where you move your polygon. So mine says 2.58. Then I want to go from B prime, or in other words, the image, to point J as well. Notice it's the same distance, isn't it? Notice the distance here is the same as the distance here. So what I want you to do is record those distances. So for mine, I would go on point B to line EF. What was it? 2.58. Okay, 2.58. And as well as over here, 2.58, right? So basically what they want you to see is that the perpendicular distance, essentially that's the distance from the image to the line of reflection, is the same as the pre-image to the line of reflection, okay? And you can do that with each of the points here. So you would want to record each point. So here I go A to G, and then A prime to G. And I should see that those are the same as well as each other. Okay, do that for each of the coordinate points for both the image and pre-image, and put the distances that you see along here. So mine was 2.57. And again, yours might be quite a bit different or a little bit different. It's okay if you get different numbers from mine, but just you should see that this is the same as this, as well as this is the same as this, and so on. Okay, once you're done with that, let's move on to question 8. What conclusions can you draw from the distances you recorded in question 7? So basically what I just said, right? That the distance from the pre-image to the line of reflection is the same as the corresponding image to the line of reflection, right? So any point on the pre-image to the line of reflection is the same distance as the image to the line of reflection, the corresponding point, right? Okay, so briefly explain that there. I already explained it a couple times. Okay, once you're done with that, let's go ahead and move on. Okay. Here's some of the things that we said earlier, but it's only written way more complicated, but basically, hopefully you understand some of these concepts. And they're showing the picture of what we just talked about here, that any point connecting the pre-image to the image is perpendicular to the line of reflection. Okay. Go ahead and meet me here on page 13. The diagram shows the pre-image ABCD and 5 reflected images. Match each reflection ABCD with its image after the transformation. Drag the items on the left to the correct locations on the right. All right. Let's start with some of the easier lines of reflection. So notice ABCD, and then I'm looking at this quadrilateral here. That's clearly reflected across the y-axis. So across the y-axis, right there. This one, going down to this one down here, that's reflected across the x-axis. So we're going to put reflected across the x-axis there. What about reflected across x equals y? So that's what we saw earlier. Remember we made EF, do that like perfect 45-degree angle there. That's going to be like this one here. Whoop. Reflected across the line x, y. What about these other ones here? So one of them says reflect across y equals negative x. So I'm actually going to show you what that might look like here. So if I reflect across, I'm going to show you the line y equals negative x is actually this line here. Okay. So which image is a reflection of that? So if I look at the distance to here, should be the same distance away. Oh, it must be this one right here. So this is the reflection there. Does that make sense? Same as like point D to here is the same to here, right? So this would be the reflection across y equals negative x. And then reflection across the origin, that's going to be this one here. When you reflect across the origin, which is 0, 0, basically what happens is it changes your x and y coordinates to their opposites, right? Okay, so it would go from like 1, 2 to -1, -2. Okay, let's go ahead and move on. So we talked about translations. Remember, translation is where it's just shifting up or down, left or right. We talked about reflections. So that's when there's a line of reflection and you're like reflecting the image on the other side of it. The next type of transformation we're going to talk about is rotations. So let's go ahead and get started with that. Here on page 15, we're going to get started with rotations. Again, we have another GeoGebra link to click on here. Okay, if you're not familiar with GeoGebra by now, you really need to be. Okay, I know it takes practice and takes time, but so does everything else that you want to get good at. Okay, question 1. Use the slider to rotate triangle ABC around point P through different angles of rotation, alpha. As you move the slider, you'll see the image A prime, B prime, C prime move on the screen. At what angles of rotation does triangle A prime, B prime, C prime coincide with each of the other triangle images? Okay, that was a mouthful, but it's actually not too bad. So let's go to this GeoGebra, and you can see down here, you should see a little green dot, and you could actually move this around. And what that does is it changes the angle of rotation of our triangle ABC. So we can rotate it, and when it comes to rotations, you need to know two things. One, the angle of rotation, and two, the center of rotation. So in this one's case, we're using point P, which is at 0, 0, as the center of rotation. Now, this is actually the most common type of rotation. Usually we rotate rotate around the origin. 0, 0 is usually what we rotate around. Okay, and this is one of those cases. So we're going to move or change our angle to coincide with each of the other triangles. So we're going to rotate, rotate, rotate until it perfectly lines up with triangle DEF. You see that there? Now notice it perfectly lines on top of it. Now what does that mean about the two shapes again? It means they're congruent, right? Remember we talked about that before. That congruent means they're the exact same shape, exact same size. So when you translate, or when you reflect, or when you rotate, the image and pre-image are always congruent, okay? In other words, it doesn't change the size or shape of the pre-image, okay? So in this one's case, for triangle DEF, we have to rotate triangle ABC, how many degrees? 45 degrees. So we're gonna go ahead and put 45 degrees here. Okay, I want you to go ahead and find the angle of rotation to coincide with triangle GHI as well as triangle JKL. Once you're done with that, let's move on to question 2. Find the distance from each vertex on the pre-image triangle ABC to the center of rotation P. Enter the values in the table. Do the same for each vertex on the other images. So what are they asking us to do here? So we want to find the distance from our original triangle ABC to point P. Okay, so we want to find the distance between each of the vertices ABC to point P. So how do we do that? Well, on GeoGebra, we want to go to distance or length. So that's going to go underneath here. You go to this tool, distance or length. Click on A, then P. Notice it gives you the distance there, 2.24. Then go B to P, C to P. All right, so then we see these distances here. So the distance from A to P is 2.24. Write that down. B to P is 5, and C to P is 4.47. So I'm going to write those down so that when I go over here, I'm just going to put those distances in. 2.24, this was 5, and this was 4.47, just like that. Okay, now then we're going to find the distance from each of these coordinate points, D, E, and F, to point P. Okay, so once again, I'm using distance or length, D to P, E to P, and F to P. Well, what do we notice about these lengths? Well, they're the same as the other, as ABC's points to point P, right? Which makes sense. When we're rotating around a point, you keep that same distance from the center point, all right? So these are actually going to be the same values here, 2.24, 5, and 4.47, okay? You can probably guess what these are, but if not, you could use that distance or length and hopefully see the pattern then. Go ahead and put those distances there. What can you conclude from your observation in question 2? So I've already kind of talked about this, but basically, when you rotate a pre-image or any shape around a center point, the distance from the pre-image to the center point is the same as the pre-image, or pre-image to the center point is the same as any of the images to the center point, okay? So when you rotate around a shape, you're conserving that distance from that center point, okay? So I want you to explain that there. Question 4. Point P is presently located at the origin. Move point P and observe how the rotated images change. Be sure that neither the images nor the pre-image overlap. Record the distances of the vertices of the pre-image triangle ABC from point P. Do the same for the other images. Round all your answers to the nearest hundredth place. That means 2 decimal places. So basically, we're going to move point P around. So go to the Move tool, and you can move point P around, okay, to wherever you like. So I'm going to move it maybe over here. Maybe I need to zoom out a little bit. Maybe I need to zoom in a little bit. I don't know. Okay. But what do we notice about the distances? Well, the distance from A to P is 4.97. Well, that's the same as D to P, right? Notice that's the corresponding point, right? And that would be the same as the distance from G to P and the same as the distance from K to P, okay? So it's kind of basically what we just said, right? That the distance from the pre-image to the center of rotation is the same as the images to the center of rotation. And again, you could see BP, that distance there from B to P, is the same as the distance from E to P, which will be the same as the distance from H to P or from K to P. Okay? And similarly with C to P. Okay, so I'm going to write down these numbers. So I have them down: 7.57, 4.97, and 7.21. Okay, now I'm going to record them here. So 4.97, and your distances might be completely different depending on how you moved your center of rotation, point P. Okay. Now, these distances are going to be the same, aren't they, right? Because these are the corresponding points on each of the images. Okay, and then so on and so forth. So go ahead and finish filling that out. And then when you're done, move on to question 5. What can you conclude about your observations in question 4? What happened as you moved point P, the center of rotation, about the coordinate plane? How can you extend your discoveries about the vertices to all points that lie on a figure or shape? So basically what we already explained. Any point from the pre-image to the center of rotation is the same distance away from the center of rotation as any of the images to the center of rotation, right? So the corresponding point from the image and pre-image are the same distance to the center of rotation along the entire rotated shape. So try to explain that as well as you can in your own words. Yeah. And when you're done with that, let's move along. Okay. Now, here we're going to be talking about some of the main rotations you're going to see. So some of the main angles of rotation you'll see are a 90-degree rotation, 180-degree rotation, and a 270-degree rotation. And there's a few rules you need to kind of know. I would definitely write these down, these rules right here, okay? Basically, when you rotate 90 degrees, counterclockwise, which is the typical way that we rotate is counterclockwise, the X and Y coordinates switch positions and the Y turns the opposite sign. Okay, that's a little bit tricky, but let's say it was 2, 3, then it would change to -3, 2. Okay. What if you rotate 180 degrees? So if it was 2, 3, what happens is both their signs change. So it'd be like -2, -3. So this is an example. Then 270 degrees counterclockwise. So that's like if it was 2, 3, what would happen is it would switch positions. So 3, and then the X coordinate changes signs. So -2. Okay. So here's like the rule. I would definitely write this down or have it somewhere, maybe save this image, screenshot it and save it somewhere. For me, I always keep, whenever I'm doing like a lesson, I have like a Jamboard, and anything I think that's important, I'll take a little clip of it and put it on that Jamboard. So then that way I have all my images, and you can just save all these images in one location. It's kind of like just grabbing notes, right? I do that all the time. So this would be something I would just like, oh, now I'm going to copy and paste it onto another sheet, and I just have them all in one location. Okay. Let's move on. Okay. So let's look at an example of how we use that. So polygon ABCD is defined by these points. Okay, great. If the polygon rotates 90 degrees counterclockwise to create polygon A prime, B prime, C prime, D prime, what are the coordinates for point C prime? So I'm going to focus right here on point C, -2, 7. And what we're going to do is rotate it 90 degrees counterclockwise. Okay, so how does that look? So we're going to be using this rule right here. Okay. So if my point was, in this case, it's -2, 7. And what happens, look at the rule, the X and Y switch positions, so 7, -2. But also the what was the Y coordinate changes signs, right? So now it's -7, -2. Okay. Dilations. So this will be the last type of transformation we're going to talk about, and that's dilations. Okay. What is a dilation? Well, a dilation is changing the size of a shape. Okay, changing its size. So let's go ahead. We have another GeoGebra. We can open here. Okay. And move this around. Notice we have triangle ABC in this case. Okay, great. What does it say? Move the slider to change the value of n. Watch what happens to the pre-image and the image of the triangle. Set n to any value you wish and enter it in the table. Then enter the coordinates of the vertices for triangle A prime, B prime, C prime. Do this for at least 3 different values of n. Okay. So let's go ahead and do that. So I'll show you what to do. So we're going to move point N, go ahead and move it to like 2. All right. Notice we're dilating. We would call this a dilation by a factor of 2. And we usually use the letter N for our factor of dilation. So in this one's case, point A on the pre-image ended up getting transformed to A prime here on the image, right? So 1, 1 ended up becoming 2, 2. So when we use a scale factor of 2, 1, 1 became 2, 2. Now what about 3, 2? So our point B. Point B was at 3, 2, but now it's at 6, 4. So in this case, B prime was at 6, 4, and C prime is at 8, 2. 8, 2, just like that. Okay, so that's how you fill in this chart. Now what I want you to do is change the value of n, maybe change it to 3, and then maybe one more, change it to 4. Okay, so we're going to change n to 3. You may have to zoom out. Okay, then put the coordinate points for A prime, B prime, and C prime. Then change n to 4 and put the coordinates for A prime, B prime, and C prime. What is the relationship between the coordinates of the vertices triangle ABC and the corresponding vertices for the image, triangle A prime, B prime, C prime? Explain the relationship in terms of n. So what do you notice here? Hopefully you already paused and filled out the rest here, but what do we notice? So notice point A went from 1, 1. Then when we use an n or a scale factor of 2, it became 2, 2. All right. What about for point B? It went from 3, 2 to 6, 4. Notice, what are we multiplying by? So 3 times what gives me 6? 2 times what gives me 4? Well, times 2, isn't it? So whatever your scale factor is, that tells you what you're going to multiply your point by in order to get to the image. So I already know if I have a scale factor of 3, this one should be 3, 3, right? And this one should be 9, 6, right? Because I'm multiplying these coordinates by the scale factor. And this one, lastly, would be 12, 3. Again, I'm multiplying these original coordinates for point C times the scale factor to get C prime. See that? So that's what I want you to state here, that any coordinate on the pre-image is multiplied by the scale factor to get the corresponding coordinate for the image. Okay. So any point on the pre-image, you can multiply it by that scale factor to get the point for the image. Okay, hopefully that makes sense. Question 3. Change the value of n some more. And observe how the lengths of the sides of the image change. Once you've settled on a value for n, record it in the table. Measure the lengths of the sides of triangle A prime, B prime, C prime. Do this at least 3 different values of n. What is the relationship between the length of the sides triangle ABC to triangle A prime, B prime, C prime? Explain the relationship in terms of n. So we could use those same n's we had before. So 2, 3, and 4. That's fine. Then we want to find the length of the sides of our image. So first, let's go back to n, a scale factor of 2. And what we want to find are the lengths of these side lengths. So the lengths of a lowercase a prime, like this side length. Now, what is that side length? Well, one thing you can do is you can go to distance or length and just click on it, and it should tell you what it is. Okay, 2.83. For B prime, it's 6, and for C prime, it's 4.47. So I'm going to go ahead and write those down. 2.83, 6, and 4.47. So then you would write these down. So for A prime, that was 2.83. For B prime, 6. And for C prime, 4.47. And I guess I should say units here for each of these. Okay. What do we notice here? What do we notice? Notice this length was 1.41, and then its image 2.83. Okay, there's a little bit of rounding error here, but what I want you to see is that to go from the length of the pre-image to the length of the image, the length of the pre-image to the length of the image, you multiply by the scale factor. Okay. 2 times 1.41 is 2.83. There's some rounding error there, so don't worry about it too much if it's not perfect, but. And then 3 times 2 gives me the 6 units. And again, 2.24 times 2 gives me the 4.47. Again, some rounding error there. But hopefully that makes sense, that whatever, to get the length, any side length from the pre-image, to get the length of the image, you would multiply by the scale factor, which makes sense, right? Now, if we change that scale factor to a 3, we should see that these values get multiplied by a factor of 3, which makes sense. And if we move the scale factor to a 4, they're multiplied by a scale factor of 4. So go ahead and finish filling out the rest of this, just how as we did for the first row. Go ahead and pause it there. Based on your observations, questions 1 to 3, what is the significance of a dilation of 0 less than n less than 1? What is the significance of n equals 1? What about n is greater than 1? Okay. Well, a couple of things here. All the scale factors we worked with so far have been n greater than 1. Now, what happened when we made a scale factor greater than 1? Like when we had a scale factor of 2, 3, 4, or whatever? Well, it made the image larger than the pre-image. So when n is greater than 1, it creates what we call an enlargement, because it makes the image larger than the pre-image. So we're going to say when n is greater than 1, what happens? The image is enlarged. We call it an enlargement. When the dilation makes it bigger, it's called an enlargement. Makes sense. Now, what do you suppose happens when n is less than 1? Say you have a scale factor of 1/2, right? That's less than 1. Well, what do you think is going to happen to the image? Well, we can actually see. If I make my scale factor, my n, 0.5 or 0.5, you can see it makes it smaller, right? So when your n is between 0 and 1, in other words, like a fractional amount, what happens to the image? It's not an enlargement, it's what we call a reduction. So the image gets smaller, we can call that a reduction, is reduced. Okay. What about when n is 1? N equals 1. The image is the same as the pre-image. In other words, they're congruent. How many questions do we have here? 3 more. Now take a look at the angle measurements for triangle ABC and triangle A prime, B prime, C prime. Move the slider and observe the values of the angles. Okay. So we're going to choose an n value. Let's go ahead and use 0.5 or 0.5. And then we're going to use an n value of, let's say, 3. Then we want to find the measure of the pre-image angle and as well as the image's angle. So how do we find the angle measures? Well, remember, we can go right here, go to angle. Then to find the angle measures, the one thing we want to keep in mind is that we want to click going clockwise. So if I want to find the measure of angle B here, I would click A, B, C. Then to find the measure of angle C, I would click B, C, A. Then to find the measure of angle A, I would click C, A, B. Now you may need to move these so you can clearly see them, like so. Okay. So on our pre-image, these will be our angle measures. So I'm going to go ahead and write those down. For angle A, it was 26.57. For B, 108.43. And for C, 45. Okay, I'm going to write those down right here. 26.57. And this will actually be the same right here as well, 26.57. Okay, so we can put the same there and there. Oh, actually, this should be for angle B. I messed up, right? Because the vertex of the angle is always the middle letter. So this is really angle ABC is actually angle B, really. So I'm going to go ahead and put the 108.43. And this should be 108.43. For BCA, that's essentially angle C. That was the 45-degree angle. And for this one, that's the 26.57. Angle CAB is really like angle A. Okay. Now, what about when we look at the image? So let's go ahead and find the angle measures on this image. So same thing, we're going to go to this angle tool. Click, 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 click. And again, we may need to move those so we can see clearly. Now, what do you notice here? Well, they're the same measures as the pre-image, aren't they? Yeah. So when we dilate a shape, it actually conserves angle measure, doesn't it? Okay. Is that true for enlargements as well? In other words, if n is greater than 1? Let's see. Well, yeah. See, the angles conserve their measurements, don't they? Which makes sense, because when you dilate the shape, you're not changing really the shape, but all its sides are still proportional. And so it keeps the same angles for each of the vertices there. All right. Hopefully you could see that there. So go ahead, and these will be the same numbers once again, right? What can you conclude about dilations from your observations, question 5? Well, just as I explained, when you dilate a shape, then the angle is preserved between the angles of the vertices are preserved, right? So each of the angles are preserved, angle measures. Okay. Throughout this activity, the scale factor n has been a positive value. However, a scale factor for dilations can also be negative. When a set of coordinates on a pre-image is multiplied by negative n instead of n, the coordinates of the image rotate about the center of dilation 180 degrees. Consider all the potential intervals of n in the table. Enter the information in the table to indicate whether the scale factor produces an enlargement, a reduction, or no size change. Also indicate whether the image rotates 180 degrees about the center of dilation. The first one has been done for you. Okay, so this is a lot of words, hard to understand exactly what they're saying, but notice let's talk about the ones we already know. So when we have a scale factor between 0 and 1, so that's like 0.5 or 0.5, remember that's a reduction, isn't it? And do we flip it 180 degrees? No, we don't, because it's positive. Between 0 and 1, that's a positive number. What about when n equals 1? Well, this is not an enlargement or reduction. This is no size change. Is it reflected 180 degrees or rotated 180 degrees, I should say? No, it's not. Again, because 1 is positive. What about when n, the scale factor, is greater than 1? Well, that's an enlargement, isn't it? Okay. And since again, once again, it's positive, we're not going to rotate 180 degrees. Now for these last three, they're all negative, aren't they? Between -1 and 0, n value of -1 and a scale factor less than -1. So for all three of these, we're going to say, yes, we would need to rotate 180 degrees. Okay. Now, similarly, this would be a reduction. So this would make the image smaller, and it would rotate it 180 degrees around the origin or center of dilation. This one, no size change. And I bet you can figure this one out. It's an enlargement. Okay, cool. Let's go ahead and move on. Hopefully that made sense. Okay. Okay, talking more about dilations. Yes. Angles are conserved. Yes. Okay, polygon ABCD is dilated about the origin to create polygon A prime, B prime, C prime, D prime. Point A is located at 1, 3, and A prime is located at 4, 12. So let's stop there. So if we look at our original, our pre-image point 1, 3 versus the image point 4, 12, what's our scale factor there? Well, it's multiplied by what? Well, by 4, isn't it? 1 times 4 gives us 4, and 3 times 4 gives us 12. That tells us the scale factor. All right, so our scale factor, our n, is 4. Would that be an enlargement or a reduction? Well, that's an enlargement, isn't it? So the polygon was enlarged with a scale factor of 4. Simple, simple. Triangle RST is dilated about the origin to create triangle R prime, S prime, T prime. Point R is located at 3, 9, and R prime is located at 1.2, 3.6. Which scale factor is used to perform the dilation? So this one's a little bit tricky, but let me go ahead and show you what they're talking about here. So we went from 3, and then we multiplied by some scale factor, and then we end up getting 1.2. All right. Similarly, this coordinate point, the y coordinate 9, multiplied by some scale factor, give us a coordinate point of 3.6. So this n, both these n's should be the same, or they will be the same. Now, one thing to ask is, well, what's the value of n? Well, hopefully you remember from all our algebra we've done, is that I can divide by 3 on both sides of this equation to go ahead and solve for n. So I'll give us that n equals 1.2 divided by 3 gives us 0.4. And this one should give us the same value for n. If I divide both sides by 9 to cancel out the 9, leaving us with n is, this would also give you 0.4. So you know your scale factor is 0.4. Okay. Hope that made sense. Let's go ahead and move along. Horizontal and vertical stretches. Use GeoGebra to explore the properties of horizontal and vertical stretches and complete each step below. Okay, so we're gonna have another GeoGebra here. All right, move the horizontal and vertical sliders to stretch the image of the triangle. When you've settled on a pair of transformed images, record the coordinates of the images in the table. Be sure to list coordinates in both horizontal, x, and vertical, y, directions. Also record the scale factors, n sub x and n sub y. Do this at least 3 times to fill in the table. So let's go ahead and make n sub x. Here we're stretching it horizontally. Let's go by a factor of 2 here. And n sub y we'll do by a factor of 3 here. Okay, so let's see. Okay, so we're changing, we want 3 different n sub x's. So let's do an n sub x of 2. Let's just focus on n sub x for now. So I'm not going to worry about n sub y. Leave this at 1 for now. Now notice, what do we want to notice here? The original point, 2, 1, what's the point of A prime here? Well, A prime, it looks like it's at 4, 1. 4, 1. Okay. What about B prime? Well, B prime's right here, 8, 2. We're going to put 8, 2. And C prime, it's right here, 10, 1. Okay. Then I want you to go ahead and do an n sub x, or a horizontal scale factor of 3, and then another horizontal scale factor of 4. So what do you, and hopefully you start to see a pattern here. I'll give you a hint. I already know this point is 6, 1. How did I figure that out? Okay. Then we're going to do the same for n sub y. So once you're done with the n sub x's, it's back. Now let's work on n sub y. So here I'll do n sub y, scale factor, vertical scale factor. I'm going to put at 2. And then let's find the coordinate points. So for A prime, it's at 2, 2. So scale factor 2. This one's at 2, 2. For B prime, this was at 4, 4. And for C prime, this one will be at 5, 2. Okay. Change the vertical scale factor to 3, and then again to 4. And see if you notice a pattern here. I'll give you a hint. This one should be 2, 3. In question 1, what do you notice about the y coordinates before and after a horizontal stretch? What do you notice about the x coordinates before and after a vertical stretch? So for the horizontal stretch, that's the n sub x. The y coordinate doesn't change. Notice from A is a 1, y coordinate, and A prime is also a 1. B to B prime, the y coordinate doesn't change. C to C prime, the y coordinate doesn't change. So that's what you want to notice there, that the y coordinates do not change after a horizontal stretch. I'm sure you can answer the next part of this. The x coordinates, see if you can answer the rest there. The second part is talking about for a vertical stretch. So that's for this n sub y. What happens to the x coordinates here? Now, what about the x coordinates when it comes to a horizontal stretch? So the x coordinates multiply by the scale factor during a horizontal stretch, or I'll say after a horizontal stretch. And that should make sense, right? We kind of see that already, right? So for a horizontal stretch, the x coordinate went from here at A of 2 to 4. Notice it multiplied by the scale factor of 2. 2 times 2 to get 4. The next one, 2 times 4 to get 8. Then 2 times 5 to get 10. So with a horizontal stretch, the x coordinates get multiplied by the scale factor. Similarly for, see if you can finish the rest. The y coordinates, finish the rest, okay? Here it says express your answer in terms of n sub x and n sub y. You don't have to do that. Move the horizontal and vertical sliders some more to stretch the image of the triangle. As you move the sliders, observe what happens to the interior angles of each triangle. Based on your observations, can you say that the stretches preserve angle measures? So here now we're going to look at the angle measures. So let's go ahead and zoom in a little bit. So let's go ahead and go to our angle here. We're going to do click, 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 to get B prime, click, click, click. For C prime, click, click, click. Okay, let's move these. Okay, very nice, very nice. Okay, great. And let's also do the same for our pre-image. Click, click, click. By the way, sometimes if you click the wrong way, like if I clicked like this, it would give me the exterior angle. If you ever end up doing that, you want to click the other way, okay? So you can undo that. So over here in GeoGebra, there's an undo, so you can do that. So what I want you to notice is, let's go ahead and look at these angle measures. Did they stay the same here? Let's see, from A to A prime, did that stay the same? From C to C prime, from B to B prime, did those stay the same? Well, no, they didn't, right? So here we want to say that when you stretch strictly horizontally or vertically, the angle measure is not conserved, okay? Let's go ahead and move on. Go ahead and move on to page 25. Let's see. All right, page 26 here, next question. A rectangle with vertices located at 1, 2, 1, 5, 3, 5, and 3, 2 is stretched horizontally by a factor of 3. With respect to the y-axis, what is the area of the image that is produced? So one thing I can look at, this one's actually kind of a pain, but I can go ahead and use GeoGebra to actually help me out. So I'm going to go ahead and I'm going to write down these coordinate points: 1, 2, 1, 5, 3, 5, and 3, 2. I think this makes a rectangle, so that's good. And we're going to do multiply by vertically by a scale factor of 3. So when we multiply by a scale factor of 3, what's going to happen to my coordinate points? Well, the y coordinates are going to get larger by a factor of 3. So instead of 1, 2, this is going to become 1, 6. Instead of 1, 5, it's going to become 1, 15. 3, 5 becomes, I'll write it over here, 3, 15, because again, we're doing a scale factor of 3 on the y-axis, so vertically. And then 3, 2 will become 3, 6. Okay. So now let's go ahead and graph these points. So 1, 6, 1, 15, 3, 15, and 3, 6. Okay. And I'm going to go ahead and go on GeoGebra, and I'm going to graph these points here. So we got 1, 6. So I'm going to go to my point tool. 1, 6, 1, 15. It's over here. 3, 15. Oh, I didn't graph these correctly. Let's go back. Okay. Let's back up. 1, 6. Let's try that again. 1, 6 is right here. 1, 15 is up here. 3, 15, 1, 2, 3. And then 3, 6 is right here. So what's created is this rectangle. Notice the length of the rectangle is 2. So this rectangle is a 2 by 9, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 by 9 rectangle. So to find the area of the rectangle, it's length times width. So that's 2 times 9, which is 18. Okay. Well, that's it for the tutorial. Okay, let's go ahead and get started with the mastery test now. So I'll give you at least a hint on each of these. By the way, if you're not subscribed already, I know most of you guys watching are not subscribed. So if you can, please subscribe. I really appreciate it. It really does help me out quite a bit. So thank you to my subscribers. Yeah. So let's go ahead and let's get started. I'll give you at least a hint on each of these. You're only going to have 5 questions. I have 10 questions here. You're going to be given 5 of these. So if you need to, just you could scroll along and just find the questions that are offered to you. So let's go ahead and start here at this first question. A triangle with vertices A, B, and C as shown. A is 0, 0, B is 0, 4, C is 6, 0, is dilated to yield the vertices A prime, B prime, C prime as seen here. The origin is the center of dilation. What is the scale factor? So the scale factor is whatever you're multiplying by to go from A to A prime, B to B prime, and C to C prime, whatever you're multiplying by, that's your scale factor. So you could look at these multiple choice here. For example, let me check answer choice D. Is this the correct answer? Well, let's see. 4 times 3, that gives me 12. Is that what B prime is? Right? So B to B prime, is that scale factor 3? Well, no, because 4 times 3 gives me 12, but this is 10 over here. So figure out which of these is the correct answer. It's definitely not that. Okay, triangle XYZ is translated 4 units up and 3 units left to yield triangle X prime, Y prime, Z prime. What is the distance between any 2 corresponding points, XYZ and X prime, Y prime, Z prime? Okay, this one's kind of a tricky one, but so basically, let's say this is X and it shifted up 4 units, so upwards 4 units. And then to the left, 3 units. Okay. Now and then here now is X prime. Okay, so that's the image. So I want to know what's this distance here. Okay, so what's this distance? I'm going to put D for distance. Well, if you might notice that I formed actually a triangle, a right triangle. A right triangle who has legs of length 3 and 4. So the way you could find this distance is by using the Pythagorean theorem. So hopefully you know that one. It's a squared plus b squared equals c squared, where the side lengths of the triangle are your A, B, and C. In this case, our 2 legs will be the 2 legs are A and B, in this case, 3 and 4. So for this one, we could say 3 squared plus 4 squared gives us c squared. 3 squared, well, that means 3 times 3, so that's 9. 4 squared is 16, and that gives us c squared. So 9 plus 16 is 25, equals c squared. And we can finish solving by square rooting both sides of the equation to get c by itself. C is 5. Okay, so that, or D in this case, right? Okay. Square EFGH stretches vertically by a factor of 2.5 to create E prime, F prime, G prime, H prime. The square stretches with respect to the x-axis. If point H is located at -2, 0, what are the coordinates of H prime? So here it's saying it's stretched vertically. So that means you multiply only the y coordinate by your scale factor. So in this case, our H was -2, 0. So if I multiply the y coordinate, which is 0 in this case, by 2.5, because again, we're stretching vertically, that means you only multiply the y coordinate. Well, what's 2.5 times 0? Well, that's still 0. So it'll actually be in the same location as it originally was. Vertically stretching won't change that point. Polygon ABCDE is reflected to produce this image. What is the equation of the line of reflection? Okay, so hopefully you can see the line of reflection is actually the y-axis. Hopefully you can see that there. Now, what's the equation of the y-axis? So the y-axis is a vertical line. And vertical lines are always in the form x equals. So it's x equals and then some number. So what's the number here? Well, x equals, it's through x equals 0. So that's going to be the equation there. Vertical lines are always x equals. Horizontal lines are always y equals. I know that's kind of counterintuitive, but that's the way it is. Okay. If quadrilateral ABCD rotates 90 degrees counterclockwise about the origin, what are the coordinates of A prime? Okay, so A is currently at -1, 2. Okay, now we want to know what's the coordinates of A prime after you rotate this shape 90 degrees counterclockwise. Well, if you remember this rule that if you have an x and y coordinate, when you rotate 90 degrees, you flip their positions and you change the sign of the y, okay? So what would that look like? Well, this goes here, this goes here, and the y coordinate changes sign. So that's gonna be -2, -1. Okay. In the image, 2 circles are centered at A. The circle containing B was dilated to produce the circle containing B prime. What is the scale factor of the dilation? So in this case, the B is the original shape. That's your pre-image. And then you dilate to produce this smaller circle. So notice how the image, the new circle, is smaller. So that's called a reduction. So when you have a reduction, that means your scale factor is less than 1. So your scale factor is between 0 and 1 in this case. So anytime it's a reduction, you know your scale factor is going to be between 0 and 1. So there's your hint. Select the correct answer from the drop-down menu. Triangle ABC is translated 6 units up, 3 units left to create triangle A prime, B prime, C prime. If vertex A is at -1, 2, and vertex B is at 1, 5, vertex A prime is at blank and B prime is at blank. Okay, so originally A was at -1, 2. Then we shifted 6 units up and 3 units left. So 6 units up, that's going to add to the y coordinate. So for the y coordinate, we're going to add 6. And to the x coordinate, 3 units left, we're actually going to subtract 3. Okay, so the A prime, so if this is A, then A prime would be at -4, 8. All right. Now, B to B prime does the same thing. So subtract 3 to move left 3, and then add 6 to go up 6. All right. Figure out B prime. A chess player moves a knight from the location 3, 2 to 5, 1 on a chessboard. If the bottom left square is labeled 1, 1, the translation made is, okay. So it went from 3 to 5 on the X. So that's 2 units to the right. So 2 right, because the X coordinate went up by 2. So that's 2 to the right. And then it went from 2 to 1 on the Y. So that's 1 down. So that translation from this point to this point is 2 units to the right and 1 unit down. Okay, so that's what you'd want to put right here. 2 units right, 1 unit down, or 1 down, 2 right, same idea. If the player moves the knight from 5, 1 to 6, 3, so on the x-axis, it went up by 1, so is that right or left? And then from 1 to 3, is that up or down? Okay. In the figure, polygon ABCD is dilated by a factor of 2 to produce the image A prime, B prime, C prime, D prime, with the origin as the center of dilation. Point A prime is at, okay, so first of all, A is at -1, -1. So first thing we need to know is where's the position of A? So in our case, A is at -1, -1. Then we dilate by a factor of 2. So our scale factor, our n, is 2. So to get A prime, what you would do is just multiply each of the coordinates by the scale factor, 2. So in our case, A prime will be at -2, -2. Okay, so that's the answer for that. Figure out where D prime would be. So the original D looks like it's at 2, -1. If I dilate by a factor of 2, what would be the coordinates of D prime, the image? Polygon ABCD is rotated 90 degrees counterclockwise about the origin to create polygon, the image. Match each set of coordinates to the vertices of the polygon to the image. Okay. So I'll go over a couple with you, but basically, if you rotate 90 degrees counterclockwise, we did one like this in one of the earlier examples, you switch the positions of X and Y, and the Y, what was the Y becomes the X, and what was the X becomes the Y, all right? And whatever was the Y also changes signs, so that's kind of tricky. So for example, actually, let's not do A. Let's actually do D. So for point D, it is at 3, 1. So D prime, I'm following this pattern here. D prime would be at, so I switch the coordinates, so 1, 3, but this one changes signs. So that's going to be -1. So -1, 3. So D prime will be at -1, 3. Okay. I'll show you another example with A. So A is currently where? Well, A is at 1, 1. Okay. So where would A prime be? Well, you switch the coordinates. In this case, they're both 1s, and then this one changes negative, right? From there to there. So -1, 1 for A prime. Okay, and then finish the rest. Okay, so that's it for the mastery test. Honestly, not too bad when you compare it to the tutorial that was, a lot of constructions and stuff. Well, with that, hope you found this useful. If you did, like, comment, subscribe, and I'll see you guys next time. Take care.